Hi, everyone. My name is Bob. I work on PyTorch, and today I'm going to talk to you about dynamic shape recompilations. I hope at the end of this talk you'll have a better intuition on dynamic shapes and how to reason about them. Okay, so what is a dynamic shape? So for this talk, we're going to imagine that we're building an LLM service. So maybe something like ChatGPT. And like most LLM service, what we want to do is we want to batch user requests together. Um, so um, a dynamic shape is a way to symbolically represent a tensor. So in this case, typically in an LM service, you have a bunch of user requests, you batch them together into a single tensor, and you run them through your network. And we can symbolically represent this batch size with a symbol, in this case, S0. And so the tensor that we feed through the network would be something like S0 by 3. And why do we need dynamic shapes? The reason why we need dynamic shapes is, by default, Torch compile does what's called a static compilation. And what this means is that every time Torch compile sees a new shape, it would do a new recompilation. So in this example, if we first see a batch size of 10, we might do a compilation, maybe that takes 10 minutes. And if we see a new batch size of 2 afterwards, we'll do another 10-minute recompilation. And if we see a batch size of 5, we'll do another one. And so dynamic shapes help to solve this problem. And the way that you can enable dynamic shapes is through the Mark Dynamic API. So the Mark Dynamic API is very simple. It takes in a tensor, and it takes in the dimension that you want as dynamic. And under the hood, what it will do is annotate the tensor to hint to our compiler, to tell our compiler, hey, in the future, this dimension we expect to vary. And so in this case, after the very first compilation, we will compile a dynamic region of code such that when we receive differing batch sizes, like 2 or 5, there's no recompilations, and we can reuse the same region of code, and we get that efficiency back. Okay. And now, what are guards? So to understand guards, let's imagine we hire a really excellent intern for our LLM service, and they came up with a really good algorithm that makes our inference much, much faster. But it only works if the batch size is divisible by 8. So a reasonable way to implement this would be to update your inference function with a conditional, where you say, if the batch size is divisible by 8, then I will use my intern's algorithm. Otherwise, I will use my normal algorithm. And this diagram gives a quick overview of how Torch compile sees this code. So the way to interpret this diagram is time is going from the top to the bottom. And what we're doing is we're feeding increasingly larger batch sizes into our model. So starting from 5 all the way up to 11. And so what first happens is when we feed in a batch size of 5, it's the first time we've run an input, so we do a compilation. 5 is not divisible by 8, so we will do the slower inference algorithm, and we'll do a compilation. And critically, we will guard this region of code with the guard batch size is not divisible by 8. Next, we run a batch size of 6 through it. It passes the guard because 6 is not divisible by 8. We reuse the compiled region. Same with 7. Now, when 8 comes around, we will have a guard failure because 8 is actually divisible by 8. And so we will do a recompilation at that point. We will compile the fast inference code, and we will guard that code with a new guard that says, only use this code if the batch size is divisible by 8. Subsequently, for 9, 10, 11, it will fail the divisible by 8 card, but it will pass the not divisible by 8 card, and so we'll revert back to the first compilation. Okay, so now we understand guards, we understand recompilations. When is it worthwhile to do a recompilation? And for this, I want you to think about the trade-off that is the most common in dynamic shapes, which is one around performance versus generality. So you can imagine that if you have an optimization that only works when the batch size is divisible by 8, that's not very general. It will only work for a single batch size. But oftentimes, due to the constraints, you can make a very, very performant kernel. In contrast, if you have a specialization that works for any batch size that's divisible by 2, it's far more general, but in practice, you'll have worse performance than a super specialized kernel. And the general equation to think about recompilations is to think about how many times do you expect to run through this specialization, what is the expected speedup of the specialization, and is the multiplication of those two greater than the compile time you'll have to incur for that specialization. So in this example, if you have an optimization where for x equals 8, you get a 20 millisecond speedup, if you invoke it 100 times, your expectation is a 2-second overall speedup. But if your compile time is 5 seconds, it's actually not worthwhile. You're going to be spending more time compiling than the counterfactual. In contrast, if you have an x mod 2 equals 0 optimization that has a 5 millisecond speedup, which is 1/4 of the previous one, but you expect to invoke it 8,000 times, it's actually a worthwhile recompilation to do because you net out ahead. Okay, so now we understand, the general trade-off between compile time and recompilations. What are some other considerations? So this is actually a real-world example we saw internally, where there was a machine learning engineer who came up with this idea to decompose matrix multiplications. And so they implemented this as an FX graph pass, where they checked the shapes of the matrices, and if it conformed to certain sizes, it would decompose it. And after this shipped, this caused some problems. So the way to interpret this graph is each horizontal line is a GPU, and each circle is a recompilation. And as you can see, the recompilations are quite unpredictable and quite unwieldy. And in a distributed environment, this is particularly problematic because distributed GPUs actually have to synchronize. They synchronize via collectives. And so you can imagine if you have 100 GPUs and one of them recompiles, the other 99 have to wait for that single GPU to finish recompiling. And this can tank your performance. And worse, if your graph is sufficiently large, you'll actually it can take more than 10 minutes, and you might actually hit nickel timeouts, which will completely crash your job and cause some reliability problems for you. Okay, so you might be thinking, wow, recompilations are really bad. How can I prevent recompilations? We'll get to the trade-off of recompilations versus not, but one way to prevent recompilations is the mark on backed API. So the mark on backed API is very similar to the mark dynamic API, except if you mark a tensor as unbacked, if at any point in the compilation we specialize, instead of specializing, we will simply throw an error, and we will point out where you're doing the specialization so that you can rewrite it in a custom op or remove the specialization. Okay. And lastly, I want to come back to this generality versus performance trade-off. If there's nothing else you take away from this talk, I want you to remember that dynamic shapes is about generality versus performance. Where on the one hand, if you use something like static shapes, you're oftentimes going to get your peak performance, but it's going to be less general. And on the other hand, you can use something like mark unbacked to get peak generality, where you will always be guaranteed a single graph, but you might not necessarily get the performance that you want. And somewhere in the middle, you have something like mark dynamic, where you can control the specialization and explore the Pareto frontier to optimize for both performance and generality. Okay, that's the conclusion to my talk. Thank you so much for coming by. This is my GitHub and X, as well as my email if you have any questions. Thank you.